so I'll get started.
I'll just go bring you chalk.
Are you going to bring me chalk?
Let you explain.
Well, thank you. Oh, I'll do 2? All right. Well, so Jade, remind me, number 2, you had t, you're given t of z was az plus b over cz plus d, is that right? No, but the original one is az, didn't it say it's...
Show the fractional linear transformation which fix the points 1 and -1 have t.
Oh, okay. I'm sorry. It says fractional linear transformation, so that means it has that formula, right? So that's what that means. And they fix the points 1 and -1. So fix 1 means t of 1 is 1, right? That's what that means, fix a point. Fix is -1 as well, right? And what else did we give? We got that t of 0 is not infinity, okay? So that's the data which you're given. You're supposed to show that t of z has a particular form, z plus funny letter divided by z times funny letter plus 1, right? And okay, so what we do is t of 1 equal to 1 gives me a plus b over c plus d equal to 1. And the next one gives me b minus a over d minus c equals to -1, right? So we have a plus b equal to c plus d, and we have b minus a equal to to c minus d, right? Multiplying through the other side. And then if you add these equations, what do you get? The a's cancel. We get 2b equal to 2c. So b is equal to c, apparently. And then once you know that, you can go back and go, okay, so then a plus b is equal to b plus d. And that gives us what? B's cancel. We get a equals to d, right? So the fact that 1 and -1 are fixed gives us a equals to d and b equals to c. Oh, thank you, Audric. After you left, I found a nub of the white. So, okay, but so then what? So then put all this in. We got what? We've got t of z is what? T of z is, I'll keep the a and the b. So az plus b divided by, what was c? C was equal to b, right? bz plus d was equal to a, right? Yeah. And so, okay, fine. Now, the problem asks you to write the formula in a certain way, right? You want to create a +1 in the denominator? Isn't that right? So if you think about that, how can that happen? That has to happen from dividing by a, right? So we divide the top and the bottom by a. Dividing by a gives us what? It gives us z plus b over a divided by, z times b over a plus 1. Now, in order to do that, I need what? I need a not equal to 0, right? So we'll come back to that in a second here. But if we let b over a equal to zeta, there you go. We've got z plus zeta divided by z zeta plus 1, which is what we were asked to show, right? So then the question remains, why is a not equal to 0? So suppose a was equal to 0 towards a contradiction, right? What would that give us? That would give us t of z equals to what? B divided by bz, right? And b can't be 0 because you're also given that this is a fractional linear transformation. So you know that AD minus BC is not equal to 0, right? So we can't have both a and b be 0. That would contradict the given assumption that it's a fractional linear transformation, all right? So b is not 0. We should cancel the b. We get 1 over z. What can you tell me about the reciprocal map? What's t of infinity? It would then be 0, right? But we're given that t of infinity is not 0, right? Therefore, our assumption that a equals 0 is incorrect. So, hence, a is not equal to 0. And there you go. That's number 2. All right. So, again, I'm I don't think it's like a bad problem overall. I just don't think what you learn in this problem is that interesting. Any other questions?
Oh, yeah. I mean, there's 10, but it's okay.
Problem 10? Yeah, let's look at problem 10. But I did.
Type definitions.
Yeah. I will project the solution number 10 here in a minute. But before I do that, let's look at an easier one, okay? So I think I said something slightly incorrect last class in terms of epsilon. Like, I do want you guys to know the epsilon delta definition for the limit. I think I said you're allowed a page of notes for the test, didn't I?
Sure, let's say that.
Should I have said that? Jade's like, I remember that clearly. That's something you said. So, okay, let's pretend it was. I mean, I may or may not have. I definitely have in the past. So, now don't make me regret that. See, because once I say something like that, then my expectation that you know the epsilon delta definition for the limit, it becomes much less ridiculous. I mean, it was not ridiculous when I first said it, but anyway, definition, right?
It's the same as Cal 1, right?
The limit as z goes to z naught, f of z is equal to L, if and only if, for each epsilon greater than 0, there exists a delta greater than 0, such that 0 less than modulus of z minus z naught less than delta implies what? Modulus of f of z minus L is less than epsilon. So yeah, this is the same as the Calc 1 definition, but there are certain questions I could ask you to like prove the limit. Here's a reasonable question to ask you guys. Some potential test questions, right? How about this? Like the limit as z goes to z naught of z equals to z naught, So that would be how would you prove that? You would use the epsilon delta definition, right?
Yeah, but there's kind of like a set rigorous way of how you do this, right? Like for the most part, like if I remember right, Cal 1, like we had like a
Yes.
we had like a list of things that
Here.
you check things off as you go.
Okay, well, I don't know if you did epsilon deltas in your Calc 1, but if you did, here's the proof. Let epsilon be greater than 0. That every proper epsilon delta proof starts with that simple sentence. Let epsilon be greater than 0. If you write this, you already have 20% of the credit with me, because 80% of the students do not write this. And for that reason, everything after they don't write this is garbage. Let epsilon be greater than 0. Choose, and I would motivate this, but for the sake of time, I'm just going to tell you, we're going to put delta equal to epsilon, right? So my delta is positive, right? Great. Let z naught be an element of the complex numbers, and suppose z is a complex number such that 0 is less than modulus of z minus z naught is less than delta, right? Then clearly the modulus of z minus z naught is less than epsilon, because I said delta is equal to epsilon, right? So what I've done, I've now showed that the difference, the distance in the complex plane between z and z naught is less than epsilon for arbitrary epsilon positive. Right? I've showed that you can select z close enough to z naught within delta units of it that make it so. And so therefore, by the definition, hence the limit as z goes to z naught of z is equal to z naught. So there you go. I think that is an example of an epsilon delta proof on your test that would be reasonable for me to ask. Something that's not too tricky. To pick the choice of delta is not too tricky, okay? We'll look at the solution to my quiz. I'll show you a tricky delta. I think I have one that's on the quiz that was tricky. But again, I also told you guys you didn't have to do that, so, I realize I'm giving you guys kind of a mixed message on that point. Sorry about that. What I'm trying to say is I would ask you an easy epsilon delta. I wouldn't ask you a complicated, sophisticated one, yeah? Now, let's get back to the open set question, okay? So the one in the quiz is kind of a pain because there's two cases and you got to fight with it, Let me work a much easier problem.
I think I showed that, like, by similarity, like, you can do both of these with one case. Because one is at x, one greater than x, or one less than x, and the other one's at x.
Well, maybe, but I would really like the complete argument and not appeals to stuff like that. So here's one. How about this? Let's see here. You pick any y you want. How about like y equals to, how about y equals to -1, right? So this defines, and let's look at the region that has the imaginary part of z greater than -1. So what is that? That's like a half plane, right?
Oh, yeah.
Yeah, I mean, it's this guy, right? Now, my claim is that that's an open set, right? So let's let z naught be an element, and let's call this set S, okay? Be an element of S, right? And let's let z naught equal to x naught plus I y naught to have a way to talk about it, right? Then what we know is we know that y naught is greater than -1. That's what we know. Now, to show that that's an interior point, I need to produce an open disk that's inside S and surrounds the point, right? Centered at the point. So you can kind of picture it. Picture's not the proof, although honestly, it's 70% of the proof. If I have a correct picture and you just don't have, all the inequalities, I still give a lot of partial credit. So what's this distance right here is really the critical issue. What's this distance?
That distance, I call it epsilon.
I know, but like specifically, what is it in terms of the point that's given z naught with x naught and y naught? How is it?
It's y naught plus 1.
Y naught plus 1 is right, yeah. So let's consider z equal to x plus iy, an element of the disk. And like you said, you're going to call that epsilon, fine. But I'll just put it down here, at y naught plus 1, right? That's my radius, centered at z naught.
You're going to see I took like stuff right over real analysis because I call it the ball.
Sure. So my argument is that that disk is in fact inside S, right? So what do we have? We have that what's by definition true about Z? We know that we're given then the distance between Z and Z naught, right, is less than Y naught plus 1, right? That's the definition of that disk. But what is this? Thus, the square root of x minus x naught squared plus y minus y naught squared is less than y naught plus 1.
Yeah.
But, of course, this, right, is greater than or equal to just the square root of x naught plus x squared. So this implies that the square root of x minus x naught squared, right, is less than y naught plus 1.
Yeah.
Because that is smaller than that, I'm writing too much. Let me repackage this argument just slightly different to show you like better notation. So note the absolute value of x minus x naught is less than or equal to the modulus of z minus z naught, which is less than y naught plus 1. That's a better way to write this, okay? We don't actually have to get into the square root of the squared thing. I mean, that's what proves this inequality, but this is something that's true. The length of the real part, right, the magnitude of the real part or the magnitude of the imaginary part is less than the magnitude of the length of the whole complex number, right? Less than or equal to. But we have strict inequality over here, so what that gives us is that minus, oh man, I've chose poorly. Do I care about x? Is this about x? It's not about x, right? X is free. X can be whatever it wants to be, and it's still an S. The issue is y, so I should have picked on y, not x. My bad. Let's try that again. So y minus y naught, like that, yeah? And then, okay, so that means that minus y naught plus 1 is less than y minus y naught is less than y naught plus 1. So then what I'm going to do is just add y naught across it, and this gives me minus 1 is less than y is less than 2y naught plus 1. The upper bound I don't care about. The lower is all I need. See, that says that y is greater than minus 1, right? So thus, z equals to x plus iy has y greater than minus 1. Thus, z is an element of S. And so the disk of radius y naught plus 1 of z naught is a subset of S. Hence, z naught is an interior point. But z naught was an arbitrary point in S. Therefore, every point in S is an interior point, which means S is open. So another way to get, so in this proof, like another way to get a lot of partial credit is to, at some point in your proof, write the sentence. To show S is open, I need to show each point in S is an interior point. And then what does that mean? That means that I have to show that at each point I can find an open disk, right, that is contained within the set surrounding the point. So anyway, I thought I should give you this example because it's better. Like your homework problem is hard because it's got the two sides you got to worry about,
I get half credit.
You only did one side. I'll probably give you guys full credit, but because in fairness to you, if I had done this in a class before the quiz was due, I would feel more vindicated and like being draconian in my grading of that problem, but
Yeah. I wrote the ball. Cleared up. X naught plus y naught.
all right, so let's do some We'll look at the solution to the quiz eventually in here, but before I do that, let's work some mission 1 stuff now that we're a little bit past it, and maybe we've forgotten the fact that we have some issues there we have to deal with, right? Let's talk about powers and logs and exponentials and all that, yeah? So let's start out real basic. Calculate value or set of values. So A, cosine of, oh, I don't know, 2 plus I. What's that equal to? B, log of, say, 1 plus I root 3. C, little log of 1 plus I root 3. So let's start out with a cosine. How would we calculate that?
I'd expand it.
You could expand it. So one way to do it would be, this is like 1/2 e to the I times 2 plus I, right? Plus e to the minus I times 2 plus I, which is what? We have I times I, so that's e to the minus 1 plus 2I, right? Plus e to the minus, well, plus 1, right? Minus 2I. Now, if I'm smart when I write this test question, I would do what? I would put I would give you instructions that is, leave your answer in Cartesian form or polar form, or I might say both. You know, leave answer in both Cartesian and polar form. So this is neither Cartesian nor polar, right? But I can work on this. This is 1 over 2 times e to the minus 1, e to the 2I, right? Plus 1/2 e to the 1, e to the minus 2I, right? Which is really 1 over, I just write 1 over 2e because I'm lazy. And that's cosine 2 plus I sine 2, and then plus e over 2, cosine minus 2, which is cosine 2 because cosine's even, minus sine 2, minus I sine 2. Which, of course, is what?
What if you had a minus theta, you minus the whole thing?
I mean, e to the minus I theta is cosine of minus theta plus I times the sine of minus theta. But sine is odd.
I mixed, sorry.
Now, group everything together. We've got, like cosine. We got cosine of 2 times what? Times like 1 over 2e plus e over 2, right? Plus I sine of 2 times what? Times 1 over 2e. Minus e over 2, right?
Yeah.
So there you go. That's the Cartesian form, because we have it's the real part plus I times imaginary part, right? So there you go. This is the Cartesian form. Now, is there another way to do this problem? Cartesian form, right? Of course, what was the other way? I bet you guys were thinking about doing the other way, right? Like the other way to go here would have been to do what? This is cosine of 2, sine of I, or rather cosine 2, cosine I, right? Minus sine 2, sine I, right? You could use adding angles formula for cosine to calculate. That's still true for complex entries. Yes, I knew that's what you meant. I did this on purpose. And my point to you is that the same answer because, and there's something to learn here perhaps. That's part of the reason I did this. Can you recognize, what is this? This is cosh of 1. See, because that's 1/2 e to the minus 1 plus 1/2 e to the 1. And this guy over here is actually sinh of 1. So this would also have been equal to cosine, and so cosine of I, right, is, well, anyway, this is equal to the same result because the cosine of I is cosh of 1, and the sine of I is minus sine of I is, in fact, sinh. Well, there's an I that pops out, right? Yeah. So sine of I is like...
That's sinh. That's I sinh.
Right. So it would be good to pin those down. That's something I would have in my formulas sheet. Like, what's the relation between cosine and sine? Cosine and cosh and sine and sinh. Yeah. Because you don't want to... There's a sign error you can make there, and there's an I that...
I think sine is equal to I sinh.
Yeah, here. Let's see here. So you want to do sine of I theta? So we have 1 over 2I e to the I theta minus e to the minus I theta, which is what? 1 over 2I e to the minus theta minus e to the theta. So bring the I upstairs, you get minus 1. So you have I times 1/2 e to the theta minus e to the minus theta. Here I use that 1 over I is equal to minus I. Something else you should know about, right? When we bring I from the denominator to the numerator, it brings a minus 1. And this, of course, is I sinh. This is something I should actually memorize, and I just keep forgetting to memorize this because this is coming up a fair amount. It's nice to know this. It's also nice to know what happens the other way around, Like sinh of I theta is what? Yeah, what's sinh of I theta? So we know that I sinh of I theta is sine of I theta by that, which means that sinh of I theta is 1 over I times the sine of minus theta, which of course is I times sine of theta. So there you go, sinh of I theta. Whoa, is that right? Whoa. Did I do something wrong? I times I is minus 1. Sine, sinh of I theta, I theta. Yeah, okay. Well, yeah.
This is I.
Let's try pi over 2. Let's see how it works. Theta equal to pi over 2. Right? Then what's sine of pi over 2? It's 1, right? What's the sinh of I pi over 2? So this is 1/2, right? E to the I pi over 2 minus e to the minus I pi over 2, which is, so we can multiply by I and divide by I, and that's I times the sine of pi over 2. which is I times 1.
Sine of pi over 2 is 1.
Okay, yeah, it works. Yeah. I thought there was a minus in one or the other of these, but.
It's sine of theta is equal to minus I sin I theta.
Oh, so yeah, I'm thinking of this as you're saying what I'm
Divide the I on both sides.
what I'm remembering is this one that come on, sine of theta is minus I sinh of I theta. That's the one I'm thinking of. Ah, okay, yeah. Anyway, there you go. Great. So can I erase some of this? I need to erase some of this.
Yeah, you can erase it.
My question to you is, okay, that's the Cartesian form. What's the polar form for this one? It's kind of awful. What is it?
Oh, the polar form?
So we've got, I'll write it out this way, cosine of 2 plus I. The easiest way to write it is cosine 2 cosh 1 plus I sine 2 sinh 1, yeah? So what's the polar form of this complex number? So the modulus of it, right, is the square root of cosine squared 2 cosh squared 1 minus, plus rather, sine squared 2 sinh squared 1. That may or may not simplify. I don't really care. All right. And what's the angle? Where is this? Well, cosine of 2 is cosine of 2 negative or positive?
Well, cosine of 2, I think it's positive. It's 1. You can add angles 1 plus 1.
Pi over 2, this is pi over 2, right?
Yeah.
Minus pi over 2. 3 pi over 2, yeah. Pi. Pi over 2 is approximately 1.57. So cosine of 2 is somewhere in here. See, so cosine of 2 plus I is, cosine of 2 is negative. And sine of 2 is positive. Sinh of 1 is positive. So roughly speaking, where this complex number is like here-ish. It is in the annoying second. It's over here, yeah? So to find the angle theta, we do theta equals to like pi minus inverse tangent of y over x. So, you know. So the moral of the story here is if I know what's good for me, I won't ask you to find the Cartesian, I won't ask you to find the polar form of this complex number because it would be such a pain to grade. But will I ask you to find the polar form of an answer? Yes, that will definitely happen. All right? Here, let me stop wasting time on that problem. So how about log of 1 plus I root 3? How do you do that?
Split it up with a natural log argument.
So by the way, just to emphasize here, the answer, the polar form would be, I don't want to, theta is given here, right? And this is equal to, you know, modulus of cosine of 2 plus I e to the I theta. This is the polar form, where I've explicitly given that as the modulus and this is the angle. Yeah, the modulus of 1 plus I root 3, right?
Yeah, plus I arg,
Capital Arg,
1 plus I root 3.
right.
And so I think we know 1 plus I root 3, that's 2.
So the length, the square root of 1 plus 3, which is 4, which is 2. Yeah, I agree.
Okay, and the argument of that variaries?
So it's,
There you go, root 3 up.
yeah, 1 over, yeah, so it's like up here. So actually, this is pi over, it's pi over 3. And the way to see that, of course, is sine of pi over 3 is root 3 over 2. Cosine pi over 3 is 1/2. So when you divide those, tangent of pi over 3 is what? Root 3. Tangent of pi over 3 is root 3. So anyway, this is, so what you told me is we got natural log of 2 plus I times pi over 3. So this right here, Cartesian form, right? What's the polar form of this one? So the polar form of this is the square root of the natural log of 2 squared plus pi squared over 9. That's the length of the complex number. And then e, yeah, I'm going to say e to the, no, not that, e to the I theta, all right, where theta is equal to the inverse tangent, in this case, of pi over 3 divided by the natural log of 2. Now, I could be wrong. I could be wrong. Is the natural log of 2 positive? Yeah, I think it's positive. Yeah, you're right, because log 1 is 0. So the natural log looks like this. This is where 1 is. E's over here, it gets to 1, right? So natural log of 2, in fact, is about 0.693. 2. Anyway, the point is, we're definitely, this complex number is in quadrant 1, so inverse tangent of the y over the x gives you the angle, the standard angle, which gives you the argument. So this right here would be the polar form. All right? Great. Now, how about the other question? What's the little log? Remember, little log is the set of values, right? Yeah. And so it is equal to the natural log of the modulus of 1 plus I root 3.
Plus little arg.
Yeah, plus exactly I times little arg of 1 plus I root 3. Or,
Well, we know that's pi over 3.
or you could just write it this way. It is the log, capital log, of 1 plus I root 3 plus 2 pi I, integer multiples of 2 pi I. So specifically, this is the set of values, you know, natural log of 2 plus I times pi over 3 plus 2 pi k, such that k is an integer. And for the sake of everything good in the world, let's not find the polar form of that set. Okay. I do not want to find the polar form of that. I mean, you could find the polar form of each element of the set if you wanted to, but let's not do that. Question?
No,
Okay.
I'm thinking about the roots here, how it's like 2 pi L.
Yes, let us talk about that. So, I should mention, we talked about complex powers, right? And when we talk about complex powers, like z to the power c, what did we say? What was z to the c defined to be? Yeah, our definition for z to the complex power was, it was Yeah, exponential of c times little log of z, right? So this is, of course, a set of values. And, but you should understand that we're also inconsistent in our notation, right? Because when I say z squared, do I mean the set of values defined by this? Is z squared? I mean, we don't actually mean z squared is exponential of 2 log of z. I don't think we mean that. I mean, if we mean that, we just got lucky. My point is, when we talk about like, we do make exceptions to this rule when we're looking at like the square. We don't think this way when we think about square or cube. You know, we revert to standard notation. So this is really something for like the ith power. And even there, you can replace little log with a particular branch of the logarithm to talk about the branch of the c power function. So let's look at an example. And we also had, and here's another exception to that notation. Z, the nth root of z, right? What was that? By definition, that was the nth root, the positive, regular, real analysis, real variable stuff, nth root of the modulus of z times e to the I arg of z divided by n. This is the nth root of z. So for example, if you wanted to take the nth root of 1 plus I, what would it be? Fruit fly. Yeah.
The nth root of 1 plus the I says 1.
Here, I'll rewrite this. This is the nth root of the square root of 2 times e to the I pi over 4. This, in polar form, is that. If you know the polar form of a complex number, calculating nth root's easy, because all you do is take the nth root of the modulus. So we take the regular plain old nth root of 2, right? And we do e to the I pi over 4n. And there you go. That is the nth root of 1 plus I in polar form. What would the nth root of 1 plus I be in Cartesian form? It is as follows. It is the nth root of 2 times the cosine of pi over 4n plus I times the sine of pi over 4n. So there you go. That would be the Cartesian form of the nth root of 1 plus I. And I guess to be fussy, you should multiply the nth root 2, so you have a plus bi explicitly. But I'm not going to take, like if I ask you for the Cartesian form and you give me a real number times something in Cartesian form, I'm going to still count that as Cartesian form because, come on. I mean, come on. Sorry. Another application of this. What if you wanted to factor z, say z cubed plus I? Factor this over the complex numbers. Can you factor it? So to factor this, what you're going to do is you want to solve z cubed equal to minus I, right?
Yeah, and then that gives you three roots of unity.
Right.
Z minus that root of unity.
So yeah, this would mean z is an element of the third roots of minus I, right? And what is that? Minus I to the 1/3, remember, is a set of values. And so that would be the principal third root of minus I, right? And then we do e to the 2 pi I over 3 times that. And then e to the 2 pi I over 3 squared times that. So you should, it would be good for you to settle in your mind, how do we calculate the principal nth roots? So I mean, this is the formula for a specific one, the principal nth root, but there are n of those.
Yeah, but you just add on 2 pi L over n. But and L is out as 0 to n minus 1.
Okay, so what is, agreed, but what is this? What is the third root of minus I? So to do that, I got to go, wait a minute, that's the third root of e to the minus I pi over 2, right? Is minus pi over 2, where does the principal, where does the argument come from? What's the values of the argument of z? Remember, minus pi less than arg z less than or equal to pi. Is that angle an allowed principal argument? It is, yeah.
Yeah, it's half pi, yeah.
So that's fine. And so with the modulus is 1, so this gives us the cube root of 1, which is, so cube root of 1 times e to the minus I pi over 2 times 3, 6. So there you go. This is e to the minus I pi over 6. And so in short, put it all together, z cubed plus I by the factor theorem is z minus e to the minus I pi over 6, right? Times z minus, so if I do e to the 2 pi I over 3, that's 4 pi over 6, right? 4 minus 1 is 3 pi over 6, 3 pi over 6. So e to the minus 3 I pi over 6, z, and then that's for 8 minus 1 plus minus e to the minus 7 pi I over 6. So I can factor using the factor theorem, right? What did the factor theorem say? You guys remember? What does the factor theorem say? It says f of c equals to 0 if and only if z minus c factor of f of z, right? That's for f of z, a polynomial. That's the context, right? That's certainly not true for like sine, cosine, exponential, other functions. But for polynomials, it's true. So there you go. We factored it. So what we did is we solved where the equation is 0 to find the roots, and then x z minus root times z minus root times z minus root gives me the factoring of it. Now, one of these things we could have found with much less sophistication, because what number cubed plus I gives you 0? Well, think about it. How about, I, right? I cubed is minus I plus I is 0, right? Where is I in this list? Z minus I should be one of these factors, is it?
Minus I pi over 6.
Yeah, it's right here, this one. So e to the, oh, wait a minute, no.
E to the minus I pi over 2 is minus I.
That gives me z plus I, though.
I thought that was weird that you weren't adding them.
No, it's minus c is a factor.
No, but you weren't, yeah, but c's minus. C's a negative number.
I mean, sorry, something screwy here.
C's a minus number, so e to the I, so when you get e to the minus 1/2 I pi, or that thing is going to be minus I, so that's z plus I. So z minus c.
Yeah, I agree that that's z plus I. That's what's bothering me. Because
But you're subtracting. You said the root should be f of c. That'd be minus I. Minus I times minus I times minus I is minus I. Minus I cubed, I think, is minus I.
my point is, if I take minus I, right, and I cube it, and I add I don't think I get 0. This gives me,
That gives you minus I.
minus,
Oh, but you get the other minus I. Yeah, I squared
Yeah, this is 2i, which means that I should be getting z minus I.
See, but you didn't add them. You like.
Oh, you know what? I see what you're saying. The problem is I took 4.
Yeah.
I said 4 minus 1 is minus 3, which is dumb. 4 minus 1 is not minus 3, it's 3. That's my error. And 8, this should be 7. Thank you. You were saying this all along, I just couldn't hear it. My bad.
It's all good. No, because we have a homework, that homework.
Oh, son of a gun. We're out of time.
A homework question with the 1 plus I to the I. Like, I got confused on
So-
whether I should subtract them or not, but I was like, that doesn't make sense.
So another common test question, guys, just before I forget. If I give you a complex number and I say find the Cartesian form of it, so I say, something like this, guys, like I say 1 plus I root 3 to the 10th power. Find the Cartesian and polar form of this.
I'll just give you the mobster.
Well, see, what you do is you just use the polar. So this is 2, e to the I pi over 3, and then, like you said, use the Mauve's theorem. So this is 2 to the 10th, right? E to the 10 pi I over 3, right? And that's the polar form of the answer, right? To find the Cartesian form, you remember e to the I theta is cosine theta plus I sine theta. So I usually ask some of these as like kind of warm-up questions at the start of the test, and like a lot of times students leave them blank, but I don't know. So I have talked nothing about complex differentiability and de Cauchy-Riemann equations today, which is foolish. That is definitely part of your test. Harmonic functions definitely part of the test, right? So, and I'm sorry we didn't look at the solution to quiz 3. I will post it so you guys can look at it.
Post a video on harmonic
And let me give you back your homework 3.
post video.
Unfortunately, so I was talking, Audric, you called me yesterday, and I, so here's your, and I was going to grade this last night, and then I realized I left them at school, but I want to give them back to you to look at, so here they are. You both got 30 out of 30 on those, so that's okay.